Okay, so today we just want to talk about some basic derivative rules. We just wrapped up talking about the derivative of sine and the derivative of cosine. I guess I should put those up here at some point. But with these are just sort of your basic rules that we'll use to manipulate things, and kind of forget their rules almost. We use them so much. But so with this, we see we have all these d over dx's. That's just read as the derivative with respect to x. Now later on when you get, well, and then k is going to be a constant term. Just a constant. U and v are going to be functions of x, so they could be anything. So if you ever see like du over dx, it means take the derivative of that function u with respect to x. So we'll kind of build up on this. But the first and one to just be really sure about is the derivative of a constant. Now, if you think about it, if you have a constant, if you have the graph of y equals 5, what kind of graph is it? It's a horizontal line, right? What's the slope of every horizontal line everywhere? 0. So what do you think the derivative of a constant is? 0. Yeah. That's it, every time, right? So that's nice. So what we're going to see is when we do big, more complicated derivatives, the constants usually just drop right off. You don't have to worry about it. Now, the big one that we use all the time is called the power rule. Some of you may know this from pre-calc. A lot of times people come in, especially if you took honors. But what this is this is, say you have an x squared or an x to the 5th. This is how you would do this. Now, this works with negative exponents. It works with rational exponents. It works with irrational exponents. Any exponent you want to put there, this will work. So it's really powerful. What we do is we take the power that we have here, which is n. We bring that down in front as a multiple, and then it's going to be times x to the n minus 1 power. Okay, so you bring the old power out in front, and you drop the exponent by 1. That's the power rule. So a quick example there would be, if I wanted to take the derivative with respect to x of x to the 5th power, I'd pull the 5 out in front. The power would be 5 minus 1, and we would get 5x to the 4th. Now, if you think of how you would do this derivative if we were still using our limit definition, you would have to have done an x plus h to the 5th power in there and expanded it, which is kind of a nightmare, right? And then get it to cancel out and then do all that work. Instead, we could just use the power rule. Your book does have, or the online book or the paper book, it does have proofs of these, but we're not really going to dwell on the proofs. We're just going to look at how to use them. So. All right, next up we have the constant multiple rule. Really makes this one even more useful. And with this, it just says if you have k times a function, right, because u is some function of x, you can just rewrite that as k times the derivative of u with respect to x. So you could basically pull the constant outside. So an example of that would be if you had the derivative with respect to x of 16x squared, right? So 16 is a constant multiple. X squared is a function of x, right? That's our u in this case. So what we would do there is you could say 16 times the derivative with respect to x of x squared. Now we should know that by the power rule, right? We're going to pull the 2 out in front, drop the power by 1. So we get 16 times 2x, which will give us 32x. Is that good? You can also see some different notation there. We'll try to look at that with some examples here in a minute. Sometimes you get the y prime notation instead of the differential notation. Last up, we have the sum and difference rule. Really like you'd hope it would be. It says if you take the derivative of u plus v, it's the same as taking the derivative of u plus the derivative of v. Or for subtraction, the same thing. So this would be the derivative of u with respect to x plus or minus the derivative of v with respect to x. So the sign is maintained. You can just kind of pull that apart and work through that. So these, again, are very, very important rules. We'll look at some examples here to look at these. Now, we also talked about as well today that the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is negative sine x. So really we have kind of 6 rules that we're looking at right now. Okay, so here we have a couple examples to look at. This is using the prime notation as opposed to before we looked at some of the differential notation. You just want to be able to kind of be comfortable with both. They both have their benefits and their kind of detractions as well. But so here we have if y equals 4x cubed plus sine y, we're asked to find y prime, and then we're going to find the second derivative because I think it won't be that big a deal. So I'm just going to write y prime equals, because again, kind of label your equations. It's a bad idea if you just have a page full of equations with no labels on them, right? We want to label them. But if we have y prime, so we know that to do 4x cubed, that's going to be 4, and I'm going to show a bunch of steps here, times the derivative of x cubed. So if you want to, you could even just put the x cubed in a parenthesis and just put the prime out of it. Just reminds me that, hey, I got to take the derivative of that before I'm done. Okay? And then plus the derivative of the sine of x, right? Because we're just using our addition property here. And then here also, we used our constant multiple property to pull that 4 out. Okay. Everybody good with that? So then, let's see, y prime, 4 times 3x squared. That was the power rule, right? You take the old power, pop it out front, reduce the power by 1, and then plus the cosine of x. So then y prime is 12x squared plus the cosine of x. That's the derivative function. There's nothing else that we can do to simplify or anything like that. If you want to, take a minute and try the second derivative. All right. Y prime, we said, was 12x squared plus cosine x. So again, we're going to use the same properties over again. So for y double prime, we could say 12 times 2x, right? The derivative of x squared is 2x by the power rule, and then minus sine of x. Then we should just clean it up, and then we get 24x minus sine x would be the second derivative, a y double prime. Okay. Yeah, we'll talk more about those later. Okay, and the next one here, this is one, this kind of shows the power of the power rule. I mean, no pun intended, but here, as we look at it, if you look back at our rules, we didn't have a square root anywhere on that whole thing, right? And if you remember with the limit definition, square roots were kind of a pain. You had to use the conjugate. It just was like a whole thing. All we have to do here is, this is a pretty common thing in calculus, is a lot of times before you start the process, if you can find an easier way to write the function, it can save you a huge amount of time. Okay, so here, if we just write it as x to the 1/2 power, it's so much easier because this is our end value now, correct? So then when we go ahead and go to find that derivative, we get y prime equals 1/2 times x to the 1/2 minus 1, right? Because we pull the old power out front, take 1 away, and then we get y prime is 1/2 x to the negative 1/2, which that's actually a fine way to write it. If you'd have to do another derivative, that would be a lot simpler. Now, we do need to know what it means, and it does have another form, right? So with that, remember, if you have a negative exponent, it means to move the base to the bottom. So other ways this could look would be 1/2 times 1 over x to the 1/2, right? I moved the x to the bottom and made the power positive, and then that's just a square root still. So it could also be written as y prime equals 1 over 2 radical x. They're equivalent. It's always good to know equivalent forms because when you're checking your work or maybe you're taking a standardized test and you need to find that. Questions with that? All right, one last example here. We're going to find the values of x where f of x has horizontal tangents. Okay, as we saw before with our graphing, a horizontal tangent is going to occur where you have a minimum or a maximum or a point of inflection, but horizontal means it's going to have a slope of 0, right? So what we want to do here is first we find the derivative of f of x, so f prime of x. Hopefully, the derivative of x cubed is 3x squared. And then minus 4 times 2x, right, because I just pulled the constant out. The derivative of x squared, you put the 2 out in front, drop the power by 1. Negative 3x has a derivative of negative 3. The derivative of 2 is just 0, right? So we get to lose constant terms all the time. So now we have that f prime of x is equal to 3x squared minus 8x minus 3. And we need to solve that for when it's equal to 0. So when does 0 equal 3x squared minus 8x minus 3? It's just kind of a word in terms of your work, which we can always get nicer work. Notice that I labeled each equation here. I didn't just start writing and not put equals anything. And then notice here when I go to solve it, I didn't just stop writing the left-hand side, but I said I want to know when it equals 0. Right? Because if you just drop the equal sign, it's kind of unclear what your intention, what you're trying to do here. So we'll factor this. I'm just going to guess and check because I know that 3x squared has to be a 3x and a 3. I know that negative 3 is the constant term, has to be a negative 1 and a 3 or a 3 and a negative 1. So what do we get? Negative 3 plus 1. Factor every one. You could split the middle. You could do a tic-tac-toe board. You could get out factoring tiles. I don't know what all we do now. But at this point, to solve it, either 3x plus 1 equals 0, or x minus 3 equals 0. So x is negative 1/3, and x is 3. So those would be the two values of x where f of x has horizontal tangents. Okay, now we'll look at, as we move forward, how to determine whether those are actually minimums or maximums or points of inflection. We will have a lot of tests to do with that. You could graph it and see, but that kind of defeats the purpose, right? So this tells you where that stuff's going on, and that's all just from a simple derivative, right? Just basically a power rule with a couple steps in it.